Very good evening, everyone. Can you guys hear me? Let me know in the chat, guys. Can you guys hear me? Thank you, Arad, for confirming how you guys are doing. How was the weekend? I think it was long weekend for you guys, right? Saturday, Sunday, both. Or you guys have any test or any guest lecture as well? Arad, Ekta, Shashan, Joseph, anyone wants to answer it? Are you guys able to hear me? No guest lecture. Okay. So it was just 2 days full on practice, fun. That's all going on. Okay. Great. Very good evening, Joseph. I hope everyone is doing fine. Today, actually, in my area, weather is little bit like summer, you can say, little bit hotter compared to the previous days or earlier days. I'm hoping everyone is feeling the same. Who is staying in near to this area, like Delhi or Lucknow or UP? So we'll wait for some more minutes, and then we'll start talking about the things. So from our last class, which I remember that on Friday, which we did, and the major topic which we were discussing on that day, that was BST. Correct, guys? So for BST, we have observed that it's a binary tree where we are going to take two childs, at most two childs, which means we any of the node which can become parent. After becoming parent, it can have zero child, one child, or two childs. That's the definition of a binary tree, right? And for the BST, it follows the same definition which binary tree has. But what the difference is here, or I would say one more additional constraint is here, that in BST, always the parent node would be greater than the left side element and lesser or equal than the right child. Correct? So the condition look like each node would be greater than left subtree and smaller or equal than the right subtree. That was the difference, or that was the additional constraint which binary search tree has given to us. Correct, guys? We have seen some examples of that also, and the reason for that is the reason for putting this constraint is it gives us better, or faster searching, or efficient. The correct word is efficient searching. We can reduce the time complexity here for our tree traversal, because earlier when we do not have BST, for finding a single element we need to traverse whole of the binary tree, whole of the tree, then only we can find it. If any element which is residing at the last label as a last node, we have to traverse everything. But in the case of BST, we can easily discard half of tree. Correct? We can, if the element which you are searching, if it is lesser than our root node, we will only search to the left subtree. And if it is not, if it is greater than the root node or the parent greater than the node, we are going to look for the right subtree. So we are easily discarding that. So that was all about the BST. And after that, I remember we have talked about the insertion and deletion scenarios. Correct, guys? So, in the what's the real life application of pre-order and post-order traversals? So, real life application, I have not think about pre-order and post-order because there would be real life application for trees, right? Because traversal is a way to go into each of the nodes, right? Like traversal, like you if you have been given a tree and you want to just go into all of the nodes, that's the traversal. So while we are traversing, they have given us three different ways: pre-order, in order, and post-order, right? So I'm not sure is there would be any real life application, because these are patterns, right? Pre-order, post-order, and in order, these are patterns, correct? So we might think about these patterns, but not sure about is there would be any of pattern which would give us any examples here, like going depth wise into tree like structures such as file system. Okay, like this. See, so same example could be for all of three, like pre-order and post-order, and as well as for in-order as well. As you can see, the one benefit which we see with the in-order in the BST, that whenever we are doing the in-order for a BST, we are already getting a sorting. We are already getting a sorted numbers there. So that could be one example for that. But I'm not sure about the pre and post. There are a lot of questions in interviews people ask, that when they like in our slide also we have one question, or might be in your exams also when you will give in the data structure exams. There you will also see that people will ask you that we have given you pre-order and in order. You need to construct a binary tree. Might be they have given you post-order traversal or in-order traversal. You need to now design a tree. These type of questions uh, comes into the exam or in interviews as well. So they just ask you about they just ask you about the way how can you write the code and how can you think about it. So these type of questions is there. So post order is important. I think all three orders are important, and sometimes mostly I have seen the examples where people are using in orders most of the time. Yeah. And compared to DFS, I have seen more example towards the BFS. Lot of problems we have tried to solve it with BFS, like level order traversal. And I think in lot of problems you use in order, pre-order, post-order. It doesn't matter. You have to just traverse it. I have seen like whatever problem I have seen till now, I have seen it like, yeah, I think you can skip it. But yeah, recursion one is easy, right? Traversing any tree through the recursionist approach, it's easy, right? So you have like post, and in order, you can easily do that with the recursive approach. So no need to like skip it through the like, yeah, for post order you can skip the iteration part if you want, if you do not want to like get it. But yeah, for recursion one it's easy, right? So you can do that easily. Okay, so let's come back to the previous thing. So I remember you guys have asked me about explanation of code of delete part, right? So anyone has tried the deletion part? Everyone was saying, I will try, I will try. I remember Arad and Joseph was saying they will try. Anyone tried the deletion of BST? So Ekta says yes. She has tried. Vishal has tried. Very nice. What about Arad and Joseph? All three cases. Great. So I told you, like, right, guys, whoever has tried it and done it, you guys can share it on LinkedIn. So others can also see it, right? I can also see the your approach as well. No problem. Yeah, please do it. I will see your approaches as well. Whoever has done it, Vishal, Arad, whoever has done it. Always got to open LinkedIn. That's that's not good. That's you can make a good habit, right? To open LinkedIn for half an hour, go and search for jobs and those things, right? Okay, so by the way, I will explain quickly the logic which we had, and yeah, let me share my screen, and then we can jump into the next questions. Okay, let me explain it. Let me show you first the code. This was the code, right? Which was we are trying to understand it in our last class. So let me quickly first go to the slide, note one note. Yeah. So let's take a very nice example and quickly. So let's take this is like I think 10 I will take. Let's create a BST. I will take here 6. I will take here 15. Let's see that. You guys can tell me if I'm missing anywhere a BST properties. Here we can take it like 12, right? Here we can take is 17, right? Here we can take it 4. Here we can take it 8, right? And then we can take it 3. We can take it 9. Yes, that will work. And here we can take it 19. Right, guys? Is it the BST or not? It's the BST, right? Yes. Okay. So what was the three cases? There was three cases, right? Case one was when we have a leaf node, when we want to delete. I'm just not writing the whole thing. I'm just quickly writing leaf node. So leaf node. If we have the leaf node, if you want to delete the leaf node like 19 or 9 or 3 or 12, if you want to delete them, just go to that node and make it as a null. Correct? Make that node as a null. That was the first case. Everyone knows that, right? You guys can just send the emoji of thumbs up. That yeah, you have understood, right? Okay. So yeah, thank you guys. So the second approach was this was the first approach. The second case, not approach, second case was when we have a single child. In the single child. In single child, there could be two scenarios. Left single or right single. Like left or right. Like you can see, it's a right, it was the right single child. It's a left single child. So if you want to delete 17, so second 17 will come into this scenario, because it has the right single child. If we want to delete the 4, it is coming into the left single child. So what we'll do here, we will delete that element and replace it with the bottom element, right? Replace it with the child element. So this 4 will be replaced with 3. This 17 will be replaced by 19, and then we will delete the 19, and then we will delete the 3. Correct? So we'll replace the values of these nodes. So 4, 3, and then we'll delete the 3 from here. Got it, guys? That was the second approach. Understood? There was a case 2, not the second approach. There was a case 2. Everyone understood? Yeah? Okay. Now let's go for the case 3. Now let's go for the case 3, which was both child. If any of node which you want to delete, if any of your node which you want to delete is have both childs. In that case, what I told you, to find it out the in order successor. Find it out in order successor. So let's see, in order successor, or see, there are two things to do that. There are two ways to do that. The first way is like if you want to delete 10 here, if you want to delete this 10 here, so what we'll do, go to the right side and find out the minimum element, which is 12 here, and replace it with that, and then delete the 12. Correct? Otherwise 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 go to the left side and find the maximum here, then replace it with that. In both scenarios, your BST properties will still not impact. Correct? But we are going with this approach where we are trying to find out the minimum element into the right side. Okay, that was the third approach, right? That was the third case. We have already discussed about this, right? Correct, guys? These were the three cases. So now let's jump into our code and let's understand what's happening. Let's take one by one example and let's try to delete it with our code. Okay, so let's try to delete 19. Let's try to delete our leaf node. Okay, try to delete the 19. Correct? So you can see in the code, we are passing a value. You can see we are, in remove, what we are calling in the remove, when we are calling the remove method, see, 1 minute, yeah. Let me first increase the size if you guys can see. Let me increase the size for it little bit. Yes. Now you can see I'm calling my remove method. In remove method, I'm passing my value, which would be 19. And then I'm internally calling this method, this dot underscore remove inner, because this method is going to be called internally again and again. So now where I'm passing value, which is 19, then I'm passing root. Correct. Now what is happening in the code? First, I'm checking if my node exists. It means if my node is not null, correct? So if my node is not null, I'm just comparing the values. So what is happening here? Let me show you the UI as well. So first I went to the root, which is here, which is 19. I'm checking, is this root is null? No, it's not. Correct? It's not. Then what I'm doing? I'm checking, is 19 greater than 10 or 19 lesser than 10? If 19 is lesser than 10, I will go to the left side. If 19 is greater than 10, I will go to the right side, because that's what the BST is. If the number which we are trying to look for, if it is greater than the node, we have to go to the right subtree. If it is lesser, we have to go to the left side. So that's what is happening in both scenarios. You can see first I'm checking this the 45 line number. For if my value is less than, I'm going, you can see, going for the left side. If my value is greater than that, then I'm going to the right side. So see guys, and you can see why we are assigning it. You can ask about this also. Node dot left and node dot right. Whatever result is coming from this function calling, why we are assigning to right. Correct? Because guys, why we are doing that? Because we are deleting here. Because we are deleting here. So right now, when we will delete the 19, so this root right subtree will change. Correct? This root, this particular node's right subtree will change. So that's why we are simply calling one by one and we are changing their left and right. Correct? See, once we delete the 19 and make this as in make this node as a null, so this 19 will be called from here. This 19, when we will move to this 19, we'll move from here. Correct? So when we will call the 19 and we'll check for, yes, we need to delete the 19. So at that time, we will delete it and return the null. And once we will return the null, we have to make this node dot right is equal to null. So that's why whatever remove inner function is returning, I'm just assigning them to node dot left right. You guys have understood this side? Assigning node dot left, node dot right? Sir, you push code in new repo, please. Sure. Push code in new repo mean you guys have that code, right? Yeah, I've already pushed it in the master branch. Okay, Hariharan. What was your question? Voice getting stuck. Is it happening with everyone? Okay, let me refresh it. Okay, two people are saying no, two people are saying yes. Little confused I am also. Video lagging. Okay. Let me refresh it. All good. Okay, three people are saying. Let me refresh it by the way. Let me refresh it. What about now, guys? Is it fine now? Yes? Okay. So you said you will write your code for this function. Yes, I did. And so I was trying to write it, and everywhere it was same. That's the way we are going to do that. Okay. And this code was also not difficult. Let me tell. That's why I'm trying to explain you. Yeah. Yes, Rian. So see, the last point which I was trying to explain here, which was node dot left and node dot right. This point I was trying to explain here. So what I was saying, Hariharan, let me come back to the notes. Once we are deleting any element from the right subtree or might be from the left subtree, so at that time we are just assigning those values which we are deleting. So right now you can see when we will delete the 19, we will be updating the 17 right. Correct? When we will be deleting the 3 from here, we will be updating also the node dot left. Correct? The this node this nodes 4's left and node 17's right. Correct? So that's why we are every time doing node dot left and node dot right. Whatever result is coming from the remove inner, we are assigning it back to the node dot left or node dot right. Understood here now? You will see with more examples. When we will delete the single element, let's just consider the single element. Like if you want to delete 17, like if you want to, 1 minute. Okay, what's happening with this? Not deleting, huh? Okay. Okay, something is not working properly. 1 minute, guys. Okay, so whatever I'm drawing new, that's not happening. 1 minute. So this is our 17, this is our 15. So if you want to delete the 17 here, guys, so what will happen? We need to update. First what we'll do? First, we'll go to the right side of it, right child node, right? And then we'll update this to 19. We'll update this to 19. Correct? We'll update this to 19. So now you can see this node's right is also changing, which has become 19. And then we'll delete this one. Then we'll delete this last node. Correct? So that's why we are updating node dot left and node dot right. Okay. Something is happening in my page. So let me first close this thing again. Let me open it again, guys. One node. Looks like these days my system is hanging out. It's hanging a lot, it looks like. Let me open the OneNote again. Yeah. So now let's see that. Yeah. You can see everything has been removed, whatever we have drawn here. Now, here I believe it was 17. Yeah. And here I believe it was 19. Right? Yeah. So we are trying to delete the 19. Correct? So what we did till now? What we did till now? So we have looked for that it's a greater, my value is greater than the value. I will go to the right side. I will go to the right side. Okay. So now, yeah. So now I will go to the right side, which is 15 now. Correct, guys? Our right side is 15, which is this. So again, we'll check. Again, we will check that is the 15 is greater than the 19, the value which we are looking. It's yes. So 19 is greater than 15. Again, go for the right side, which is 17 now. Correct? So again, we'll look. Is 17 greater than 19? Yes, it is. We'll go again to the 19. Now we are at this node. Now we are at this node from this function. Till now, we have only ran this function. Till now, we have only ran this 48 line because always my value which we are looking, it's greater than the node value. That's why we are continuously going to the right side. Now when we will call the same remove inner function for 19, so first we'll check is value less than node or value? No. Is value greater than node or value? No, because 19 is not less than 19. 19 is not greater than 19. So it will go for the third condition. Is 19 have any left and right? No. You can see that 19 does not have any left and right, right? So it will not go into the else if condition. So it will go into the last condition, which is else part, where we are, what we are doing, we are assigning node is equal to node dot left or node dot right. And in this case, both are null. Node dot left is also null. Node dot right is also null. Right, guys? You can see here, 19 does not have any node. Node dot left, node dot right, both are null. So what we are doing, we are returning this null from here. We are returning this null from here. And this return will go where? To this line, this dot underscore remove inner. So right now, how we reach to the 19? We are reaching from 17. So 17 right will also become null. 17th right will also become null. And once the updated 17 will be updated to 15th right as well. And updated 15th will be updated to 10th as well. And that's how our loop will stop. And that's how our loop will stop. Understood, guys? The deletion of 19. Everyone understood? Yeah. So now let's go quickly for the like single child as well. Now let's go for 17. Was it looking difficult, Hariharan or Suraj? Now let's go for the 17 also. So for 17, again, same logic will work first. It will go for 10. It will go for 15. It will go for 17. Here it will be coming to the, for 17, it will go to the, again it will come to the last condition. And this time, it will again look for if node dot left or node dot right. So in our case, 17 does not have any left. In our case, 17 does not have any left, so it will return null. But it has it has one right, which is 19. So what I'm doing here, I'm simply returning 19 directly. You can see I'm simply returning 19. So I will return that node which is located here. So now you can see the 17 will be removed and 19 will be added directly to 15. From where we are coming to 15? We are coming from here. Correct. So now it will be so first 19 will be written from here, and then the 17 will be coming. The 15th right will be changed from here. Guys, for this case, we have simply going to 17. We have not gone to 19, right? So directly we'll update the 15th right subtree, and then we'll update the 10th right subtree. Understood? The single child as well. Single child and no child was similar, right? We are just returning left dot right and left dot null. When we do not have any right and left, we are simply returning null. When we have any right or left, we are returning that node. So that's what. Okay, guys. So now let's look for the last scenario, which is the both child. Now we'll delete 15 or 6. Let's go for left side also. Now we are deleting 6. So we'll start again from the 10. You can see, we'll start again from the 10. Again, we'll check, is value less than node dot value? Yes, because 6 is less than 10. So we'll go to this side. We'll again, now we'll be reaching to 6. Now we are at the 6th node. Correct? So now we'll check for 6. Is it less than? No. Is it right then? Is it greater than? No. Does it have left or right? Yes. 16 has left and right. So what I'm doing here, I am finding out the min value on the right side. I'm finding out the min value in the right side, 8 and 9, right? So now you can see for my finding min value, I'm using this method. First, what I did, I find it out. I've taken first node as a minimum value. So you can see 8, I've taken 8 as a minimum there. Correct? I've taken 8 as a minimum there. And then I'm just simply looping, I'm just running a loop on the left side. On the left side, because we are looking for in order successor. And in order successor is left node, left root and right. So always minimum will be at the left side. So that's why I'm checking. But in our case, we do not have any left. You can see 8 does not have any left. So minimum would be 8 only. Minimum would be 8 only. So then what we are doing, whatever minimum value is coming, I'm just first assigning node dot value as a 8. Node dot value is 8. So this 6 will be replaced with 8. Now we need to delete this 8 as well. Now we need to delete this 8. So I'm again calling remove inner. You can see I'm again calling remove inner, and I'm passing node dot value, which is updated value 8. I'm looking for 8, and where I'm looking, node dot right. So I will be again going into the right side, and I will again look. It will become a single child scenario now. 8 and 9. It will become single child scenario. So 8 will be replaced with 9. 8 will be replaced with 9, and 9 will be removed. 9 will be, come, eraser is not coming here. Yeah, and 9 will be removed. Understood? Understood both scenarios? Code was not difficult at all. And I find it this code everywhere, same code. Okay, guys. So that was this question. And I remember one question you have also asked. That was why we are always like, I think that question was for a deletion in binary tree. Deletion in binary tree. That why we are again always going into the uh, the last label, right? So everywhere I was looking into it. So everywhere I was finding the same answer. In the binary tree deletion, we always have to look for last node at a last label. Last node at a last label. That's what every time we need to look for in binary tree, and we need to delete that. We need to replace that node with the deletion node in the binary tree. You remember, right? If we have any element in the middle, we need to like if we want to delete any element, so we need to look for the last node in the last label. We need to replace it with that, and then we need to delete the last label node. Remember that you guys have asked the question there. So I always find it out. Yeah, even what like whatever is the last node, if it's the left side, right side, doesn't matter. You just need to look for last node at last level, and you need to delete it. So that was the two questions I remember. You guys have any other questions from the previous class? You guys can let me know right now. Joseph is saying some right view. Okay, Ekta has a question, doubt for right view. By the way, we have a revision also, so it would be better. We can go for this one in the next revision class as well. But if you have like some small doubts in that, I can quickly answer that. If you like want to explain whole code, I will just do that right now. So for right view or for sum for all nodes. Okay, not now. Okay. So sum for all nodes. That was the last question, right, Joseph? Which you are doing it. Yeah. So that was the last question, guys. Where is that? Yeah. So when we started solving the problem, so this was the last question which we have discussed before Saturday's like before yeah, on Friday's class at the last time. And that was question was, given the root of binary search tree, convert it to the greater tree such that the every key of original BST is changed to original key plus the sum of all keys greater than the original key in BST. So like if I talk about this 5, so you just need to find it out all the greater keys in this whole binary tree, binary search tree, and you just need to add all of them, and then update this 5 with the sum of all the greater keys into that. Greater and equal. 5 is equal, so that's why 5 will also be added. So now you can see that all the greater or equal keys to 5. So 5, 6, 7, 8. These are only all the greater and equal keys to 5. So you just need to add all of them. So you can just add 8, 7, 15, 21, and 5, 26. So that's why you will replace it with 26. And that's why every node you can look into that, and you need to do the same for every node. Okay. Did you guys understood the question now? Everyone understood the question? Yes, so we should replace value 5 with sum of all the values of no, all no, not all the values of nodes, all the greater or equal nodes, the sum of all the greater or equal nodes. Okay, Harsa, we need to add all of them, and then we need to update the value with that. Okay, so now what I told you, what was the approach I told you? Because it's a BST. In BST, we know that all the greater values are always onto the right side. All the greater values are always on the right side. So what you need to do, if I start from 8, if I start from 8, so you can see this is my node, right? So all the greater value will always be into the right side of 8. All the lesser values will be on the left side of node. So always what we need to traverse first? Onto the right side. Correct? So you can see for a single node, let me go back to one node. For a single node, guys, if I have a single node and if I want to do the similar thing, what is this? Huh? I can remove them. Yeah, okay, I can. Okay, yeah. So, guys, for a single node, like if I only talk about eight, right? So, if I want to find out the same answer, so what the question was asking, you need to find out all the greater or equal node, greater or equal node. So, greater node will always be on this side. Greater node will always be on the this side, and equal node will be the same node, right? Equal node will always be the same node. Correct? So that's why, guys, you just need to start traversing from the right side and add it to the root value, add it into the node, add it into the node. So if you are traversing for 8, traverse all the right side and add it into the 8. Correct? Understood? Everyone understood this thing? We will traverse all the right side elements and we will add it into the root, the node which we are looking right now. Okay, so if we start from 8, yeah, so if we start from 8, where is it? Yeah, okay, yeah, so if we start from 8, so because there is nothing on the right side, so we'll consider that as a 0. We'll consider that as a 0. So 8 plus 0 will be 8. Correct? So for this, answer would be 8. Correct? So we'll take one variable here. We'll take one variable here, sum. Correct? We'll take sum here. And we'll take it as a 0 first before starting our loop. And so first we'll go into the rightmost element, which is 8. And you'll find that it does not have any left, it does not have any right. It means we just, because it does not have any left, it does not have any right, so we'll just return 0 from there, and then we'll add into it. So now 8 will be replaced with 8 only. Correct, guys? 8 will be replaced with 8 only. Now we'll go little bit further on the back side, which is 7 now. Correct? That's what you can see in the slides as well. 7. Correct? And right till now, our sum till now our sum has become 8 because we have already added 8 here. Now for 7, all the right side values sum is 8. So we'll add it here also. 7 plus 8 will become 15. So it will be replaced with 15. Now we'll go a little bit above, which is 6. Which is 6. So till now our sum has become 15. Till now our sum has become 15. So once we'll reach 6 again, we'll add this with this, because this sum is nothing. It's the sum of all the right side of it. All the right side of it. So once we reach 6, we just need to add it with this. So this 6 will be replaced with 21. So after that, you can see, guys, we are looking for right side, then root. But now if we have any left side also, so you can see we will also go for the left side, which is, what was that? Which is 5. Which is 5. So you can see how the traversing is happening. Again, once we reach 5, all this, whatever we have, whatever sum we have, just add it into it. It will be replaced with 6. So you can see 3 things are happening. Right. First we are traversing right. Then we are going into the root. And then we are going into the left side. That's what happening, guys. Right, guys. First we traverse 8 right. We do not find anything. We just added 0. We just returned 0 from there, added into the sum. Then we again go for root, which is 8 itself. We have added 0 into this 8, so sum has become 8. Then we went to the left side. It was 0 again. So 0 plus 8, again 8 is there. Then we are going to do the 7. Because you can see the 7 is right side. So right, left, left. Then we are doing this addition. Understood, guys? Can you guys guess what this traversal is? Right, root, left. What this traversal is this traversal is matching with any of them? Any of the traversal which we have already read? Right, root, left. Yes, it's the inverse in order. Because in order, we do left, root, and right. But here what we are doing? Right, root, in order, right, root and left. So that's the same code. We just need one variable to track the values. And that's what, let me show you the code for this. Code was very easy. So 1 minute. So the code for this would be greater tree. Yeah. You see, very simple code. If root dot right to first traverse all the right side. Once we reach to the right side, take a sum variable or pre variable, add the root dot value to the pre plus root, and you can see I'm also updating the root dot value. Means same node. I'm doing two things. I'm updating my sum variables as well, or the same root value as well, and then I'm going into the left side. Once whole traversal is done, return the root. It was easy, right? Everyone understood? Understood, everyone? Any questions? Once again, okay. So code part. Okay, once again code. So you can see, Arat, we are traversing right side. Once we reach to the right side, we are updating our sum variable and that root value. That root value, and you can see pre plus root dot value. It would be uh, it would be like 0 plus 8. You can see pre is 0 and root dot value is 8. Correct? So we will update that sum as a 8 and root dot value also as a update as 8. Once we have already traversed right, this is root traversal, and then we are going to the left side. Already done that, right? In order, pre-order, and that one. So we are moving to upwards from right. Yes, we are moving from there. Right, then root, then that. Correct. Yes. Line number 4. So line number 4, you can see this pre is some variable and root dot value. You see these things we are adding, right? Sum is equal to 21. So this is sum is pre. Sum is nothing, it's a pre. This sum is pre variable. And root dot val is 7, 8, and 6. That's what, Ankit. So we are just updating our sum value as well and the root value as well, because we need to update both things. We need to create a greater tree. We need to update both things. Understood, Ankit? In line number 4, we are doing both things. We are assigning to the sum as well, and we are assigning to the root dot value as well. Both lines. Both things in one line. Sure, Ekta. Are we good now? So once we are reaching to the right of that node, we are stopping it there. Then we are adding the value, and then we are going to the left side. Are we good, guys? And then we are going back to the previous route. Then we are again traversing right, left, going into the same way. Yeah. Okay, so these were the two questions. In that slide, let's see remaining questions from that side. So right view. So you guys want me to explain the right view also? We can go for that as well, no problem. Otherwise, we can go for the next question, which was this one. Given a binary tree, check if it's a BST or not. I think I already explained you the logic for that. But if anyone wants me to again explain it, you guys can tell me in the chat. I told you about the range portion, right? If you guys didn't remember, I can tell you again. Can you guys let me know in the chat? Or we can move to the next question once more. Okay. Checking BST1 was easy. Yes, it was. Okay, Arad, okay, let me quickly explain it because the next question is also depending on that. So let's do that quickly. Yeah. So let's take a BST quickly. Let's take the similar one. which we have in the question, which is here 135. Let's draw this. Let me draw that, yeah. So 5, 7, 3, 1, 4, 5, and 6. Do not take any duplicate elements right now. We just take this one, yeah, to better understand it. Yeah, just take it to the right element. Yeah, my drawing is, yeah. I think this is little bit lagging today. Not sure why. So see, guys, what I told you about a BST, it's I started talking about the range concept, right? I started telling you about the range concept. Correct? What was that range concept? I told you start from the root node. Start from the root node, because what would be the range for this root node? It would be between minus infinity to infinity, because root node does not have any conditions. In the BST, for for making a BST, first node we can take any numbers, right? So that's why for the root node the constant is minus infinity to infinity. Any number between that we can take it. Understood, guys? For root node, everyone understood for the root node? Yes. So now let's look for the left side. What is the constraint for left side? The constraint for left side is the left element will always be smaller than 5. Left constraint is always the left subtree will always be smaller than the root. So that's why for 3, the range would be minus infinity to 4. Correct? Any number between minus infinity to 4, including 4, can be the left side element. Correct? And for the right side, the right for right side, the range is it should be greater than 5. So it would be 6 comma infinity. Correct, guys? That would be the range for the 7. Any number could be between 6 and infinity. Correct? Or equal to 5. Or equal to 5 as well. Yes, if you are considering the without duplicate elements, yes, equal to 5 as well. Okay? Now, what about the 1? What about the 1? So for 1, it would be minus infinity to uh, 2. Correct? Minus infinity to 2. Am I right, guys? For 1, will that make sense? Minus infinity to 2. That does it make sense, guys? Because it's the lesser than 3. It should be lesser than 3. Correct, guys? What would be for 4? What would be for 4? What would be for 4? What would be the range for 4, guys? So it should be between, I would say, 4 to 4 to uh, 4 to 4, I would say. Yeah, it would be between 4 to 4, because we can't take 5 as well, because it should be lesser than that. Correct? For 4, it should be 4 to 4. We can't take the maximum of it. Yes? And same for 6. Same for 6. I believe this would be 5 to 5 to. I think this 6 will not come here, right? Because see, all the subtree elements should be minimum, right? All the subtree element, all the left side element should be smaller. Correct, guys? So I believe This 6 will not, 6 could also not come here. Correct? So let me remove this one. So the like we can take another number here, which I believe it could be. Well, there could be any other element. No, right? We can't take any element here, right? So this should be this much only. Yeah, 4 we can take. Yes, for equal scenario, yes, 4 we can take again. So not understood the fourth case. So Hariharan, what I'm saying, our left side condition is that always the element should be smaller than the smaller element, right? And the right side element should always be greater. So for 4 which is coming from the 3's right. So the minimum range would be 4 for it because it should be greater than that. It should be greater than that. And the maximum range could be lesser than this. Lesser than this. So that's why I'm taking 4 here. That's why I'm taking 4 here. Understood? So that's what actually it's happening in code as well. Let me show you in the BST, or where was that code? Yeah, is valid BST. Yes. Even see, that's what happening in the code as well, guys. So these are my base conditions. If my node is null, just return true from there. If my node dot val less than minimum range or greater than minimum range, greater than the maximum range, I have to return false because that cannot come in the BST. And you can see how I am passing. If I am if I'm passing my root node, if I'm passing my root node, which is in this case it's 1, right? In this case it's a 5, sorry, in this case it's a 5. So for 5 you can see I'm passing number dot min value and number dot max value, which is minus infinity, which is equal to minus infinity and the plus infinity. Correct? Not equal to, but just close to that, we can say, because these are the maximum or minimum number in JavaScript. Correct? I'm not saying these are infinity. I'm just saying close to minus infinity and close to plus infinity. Correct? For 5, you can see. So first time these condition will match, right? First time these condition will match. Node is null, no. Node dual less than min, no. Node dual greater than max, no. It will go into this part. Then what I'm doing for left side, I'm passing my min as like that only, minus infinity, and I'm passing my max as node dot val minus 1, which is 5 minus 1 is equal to 4. So I'm passing minus infinity comma 4. For right side, for right side, you can see for right side what I'm passing, node dot val plus 1 and then max. And that's what continuously it will happen for each child. Every time max will change and then min will change according to that. Okay, guys? So that will happen. Yes, all these codes are there. Yes, all these codes are available in master branch. Yeah. Okay, guys. Now let's move into the next question. Now let's move into the next question, which is also interesting and which is little bit related to this one only, which is the problem 3. So they are saying they have given us one pre-order traversal. They have given us pre-order traversal of BST, and we need to find the leaf node of BST. We need to find the leaf node of BST. And they are saying, if you will read the real questions like in the websites, so they will say that you do not need to construct a tree. You have to like think something while traversing an array. While traversing a single array, you need to give us the solution. Otherwise, you can simply construct a tree with the help of pre-order traversal, and then you can provide the node. But no, they are saying no, that's not right. So see, if you have to simply construct a tree, it can be like this, right? Let me show you. If I take this 890, this is our example, right? 890, what's happening, guys? 890, 325, then 290, right? Then 530, and then we have 960. Correct? These are the five numbers or nodes you can consider they have given us. And this they are in the pre-order. Correct? They are in the pre-order. Okay. It's not good. Pre-order, yeah. So guys, first tell me what is the pre-order concept? What is the pre-order concept? What is the pattern we need which we follow in the pre-order? So in the pre-order, we follow root, left, right. Correct? So always the first element will always be root. And always, because it's a BST. And guys, always remember this question is for BST. The tree which we have, it's a BST. So always in the BST, you always know that all the lesser element will always be on the left side and all the greater element always be on the right side. So that's what you can see here. This is our root because we know that in the pre-order, a first element will always be our root. So this would be root, and always all the lesser element will be on the left side. So you can see 325, and we are not sure about these things, but we will see that 325, 290, 530. These will be on the left side, and then will be on the right side. We know that, right? And then we can again do this here. We can again do this here, right? So 325, we can again like construct the tree from here as well. So 325 will be again our root. 320, okay, very weird. Today actually, I'm not sure why my marker is not working properly. So 325, okay, very weird. So 325 will be our root and 290 will be here. Uh-oh. And then we have 530, which is greater than that. And then 960 here. So you can see three root nodes are coming here, 290, 530, and 960. And that was our answer as well. You can see that was our answer as well, 290, 530, and 965. Correct. So if we have to construct a tree, we can simply do that. We can just simply do the reverse and create a tree, and then at the end we can find the leaf node. But we do not need to do that. So we have to traverse our array in a way so we can get our result. So we can get our leaf node. Okay. So we are going to use, guys, that same logic of leaf and range, the same range logic, because it's a BSC tree. So we are going to combine two logics here. One is the pre-order, where we are going to look for root, left and right. And then we are also going to use the range logic from our previous question. So, okay, so now let's try to solve it. Okay, and I will also open the code so you guys can also see the code. You can parallelly see both things. Yeah. So for that would be code would be leaf node. Yeah, this is the leaf node code. Correct? Okay. So this is our leaf node code. So what we'll do, guys, let's start from the So what we'll do, guys, we'll first take uh, a global variable as a I, which will help us in our traversing, Okay. So we have designed it I as a 0 here. Now we will start traversing our array. So first, what we'll do, we'll take 890. We'll take 890. So now I will draw it in the middle. So 890 is there, right? And I is 0 right now. So I also write I is 0 here. Correct? I is 0 and 890. So now what I will do, I will call I will pass this 890 for, because see, uh, this is my 890 and I will check that is 890 is coming under minus infinity comma infinity, because that was the first condition, right? That was the first range which we have to pass it to consider is my root node. And by the way, we already know that this is a pre-order, so this is a root node. So that's what first thing we'll check this thing. So you can see here, while I'm calling my pre-order, you can see find leaf node method is there, and I'm passing my pre-order array here, and I'm passing again min value and max value, and I'm writing it as a main, because main method, like the main value or root method is right now it's calling. So you can see here. So that's what is happening. Correct. So first time we are passing min and max. Okay. First time for root we are passing this. Now the next time we have to now check for 325. Is 325 is on the left side of it or in the right side of it? So what we'll do, guys, we will call both. So first we'll call left side of it, and we'll increase our i's value. We'll increase I value to 1. We'll increase I value to 1. We'll increase our I values to 1. So now, because we are looking for first element now, that's why I value is 1. This I will only help us to traverse this array. It's not going to help us any other place. So I is equal to 1. So from 890, I'm calling for 325 with this range. For left, always range would be minus infinity, comma 890. I'm not taking minus 1 this time, guys. I'm just taking minus infinity to 890. Okay. I'm taking same. Let me check. Is they are doing minus one also? No, they're doing it. They're just simply taking pre I minus one. Yeah. So I'm just simply taking 890 this time. I'm not taking 889. I'm just taking 890. Okay. So I'm calling with this range to whom? 325. I'm calling with this range to 325, which is on the left side. Understood this thing, guys? Let me come back to chat. Understood this thing? From 890, I'm calling now 325, nothing next element. And my range should be minus infinity to 890. So minus infinity, yes. So this element is between this? Yes, it is. This element is between this? Yes, it is. If it is, then we are okay. Then it means 325 is the left of it. So we are okay. Now we'll go for the next element. Now we'll go for the second element. Is again it's a left element or not? Again it's a left element or not? So now again we are again calling left. We are again calling left with what range? Can anyone wants to tell me with what range? Minus infinity to 325. Correct, guys? And now we are checking to whom? 290. And right now you can see here i's value was 1, here i's value is 2. Correct, guys? Understood? Where I value is 2, we are checking for 290, and our range is minus infinity to 325. Are we good, guys? Are we good? Yeah. So now 290 is again in the range of these two. 290 is again in the range of these two. So what we'll do? We'll again call left. Will again call left, and you can see that, right? 325, 290, all of our the left of 890. So that's why we are calling again and again left. So again we are calling left, guys, and we'll change our I value to 3 now. Change our I value to 3. Now I value will become 3, and we are now checking for third element, which is 530. And with what range, guys? With what range? Minus infinity, say 290. Correct, guys? Minus infinity to 290. Correct? We are checking for minus infinity to 290. Am I correct? Anyone missing anything till now? Let me know in the chat, guys. Anyone is missing till now? Okay, let me show you the code also and read only code till that. You can see, I'm just, so you can see here, these are my consoles. So I'm just checking, just ignore all these lines till now. Just first this condition. If pre of I, pre is my, the array, pre-order array, and I'm checking pre of 0 greater than min, pre of 0 less than max. So this is for root condition. Then I'm increasing my ith value. Then I am calling is leaf again for left side only. You can see for left side. So I'm passing min as minus infinity and I'm changing my max range because you know that for the left always the max range is changing. So that's why I'm calling it a left. And then I'm calling right side as well. But till now we have not called right side while I'm explaining. But we have to call left and right both sides. We have to check any number which we are going to assign. Is it going to be left side or right side? Anywhere it can go, right? So that's why we are checking left and right. Anyone has any confusion till now? Can we move further? Yes? Okay, let's move further. So now let's see that from 290 we have called left side for 530 and which is not in the middle of it, right guys? So we will be returning false from here, correct? Will be returning false from here. And you guys, can you tell me what is the condition of leaf node? What is the condition of leaf node? Leaf node are those node which does not have any left child and right child, which does not have any left child and right child. Correct? Just remember this condition also. Yes, left and right both should be null. Okay. So now you can see, guys, while we are trying to assign 530, left has given us false. Left has given us false. Now let's go for right side. Now let's go for right side. Now let's go for right side. Let's check. Might be 290 can come between 290 can come on the sorry 530 can come on the right side of 290. That could also possible, right? There is a possibility, right? That 530 is not coming on the left side. It could come on the right side. Let's check that as well. Let's check. So what would be the range we are sharing here? What would be the range here? So the range would be, guys, here minus, no, not minus. Because while we are going for right side, so min range will change, right? Min range will be changed. So it would be pre I minus 1. See, every time for taking the range, I am taking pre I minus 1. Like the previous value. Wherever at whatever index we are right now, just take the previous value for range. So you can see while I was on 290, while I was on 325, sorry, while I was on 290, I was using the pre, which is 325. Correct? When I was looking for I is equal to 3, I have taken I is equal to 2. Still we are I is equal to 3. So our minimum range would be 290. Minimum range would be 290. Correct? And max would be 325. Correct? With this range, we will be looking for 530. Am I right or not? Will this range on right side, we will be looking for 530. You guys tell me, are we doing wrong or correct? Guys, the min would be 290 and the max would be 325. The max is coming. You can see I have drawing. I have whole drawing, right? Yeah, I have the drawing, right? This is min and max, right? You remember that. This is min and max. Every time, that's why I'm drawing it, min and max. And again, guys, from here, we will be returning false because 530 is not between them. Correct? Again, 530 is not between them. Correct? Again, 530 is not between them. So first thing, no, before, yes, we will definitely go up. But before that, what we'll do, we will check if in any of the node, left and right returns false, That means it's the leaf node. That means it's the leaf node. We will print it out. So that's what you can see in the code, guys. That's what I'm doing. After finding out left and right, if both places I find it out as a false, I am just printing that answer. I'm just printing that answer. Correct? And returning true from there. Returning true from there. Correct? So now you can see that from here left and false, both are returning false. Both are returning false. So I will be returning here true. Correct? Now we'll go for this right. For the same element 530. Am I right or not? Now we will go for this element. Correct? Everyone understanding these things or not? How we printed out the first leaf node? Everyone understood or not? How we printed out the first leaf node? Okay, now let's move further. Again, try to look for. We are again looking for right side. And what is the code for right side? Pre I minus 1. Pre I minus 1. Comma max. Pre I minus 1, comma max. Correct. So first, let's say, so first tell me for which element we are looking for, which is I is equal to 3 and our element is 530. Now let's talk about the range here. So what would be the range? The first value. The first value would be pre I minus 1. I is 3 right now. So 3 minus 1, 0, 1, 2. It would be 290. It would be 290. And the next element would be, the max range would be 890. Max range would be 890. Which will be coming from here. Which will be coming from here. So the min and max range would be 290, 890. And here, guys, it will pass because 530 is coming between them. 530 is coming between them. Correct? So 530 is coming between them. So what we'll do? What we'll do? We will be saying it as a true. No. Yeah. Okay, first tell me, did you guys understood the range part? See, according to logic which we are going there, that logic is saying that pre I minus 1. Pre I minus 1. With that logic, our range should be 290, not 325. The minimum range, it should be 325. The minimum range which should come here, it should be 290. You can see the logic pre I minus 1. So that's the range which we are looking here, 290, 890. Okay. Now, guys, you can say that between these two, 530 is residing. Correct? 530 is coming between these two. Yes. So now what we will be doing here, guys, we will be increasing our value of 3. We'll increasing our value of I, which will be making 4. And again, from here, we will be calling left and right. Left and right. First, we will be calling left, not right. First, we will be calling left. Okay. First, we will be calling left. Okay. So now I has become 4. We are looking for which element? Which is 960. We are looking for 960. Correct? And now tell me about the range. Now tell me about the range. Again, pre I minus 1. Pre I minus 1. So right now we can see it's a 3. See, guys, we are deciding range based on the I. For this code, we are deciding the range based on this I value. So again, pre I minus 1, which is 3. Right now I is 4. I am pre I minus 1 3. What is that 3? 0, 1, 2 and 3. Yes, so it's the 530. So now the range would be here. Yeah. So now range would be here min comma 530. So min is 290. You can see the min is 290. So now here would be 290 comma 530. Correct? Min is 290 and max, which we will be defining with pre I minus 1, which will be defining with pre I minus 1. Oh, not able to write the 1 there. Huh? 1 minute, guys. It's lagging. Huh? It's lagging too much for me today. Yeah. So pre I minus 1, which is 530. Again, you can see that it will be returning as false. It will be returning as false because 960 is not residing between that. 960 is not residing between this. So now next we'll go for right side, guys, which the range would be um, uh, so range would be pre I minus 1, which is 530, and max would be 890. Again, I is equal to 4 and 960. Again, guys, again, it is going to return false. Both places, it is going to return false. And again, we got the second 530 as a second leaf node. First, we got 290. Now, 530 is going to be the second leaf node. Okay, guys. Now 530 is going to be second second leaf node. Sir, we are using recursion, so I should be reduced to its previous value when we are returning. So range for 530 should be 325 to 890. Yes, actually, we can do that. We can see right now what we did. So with that, actually, there is one confusion. If we will see, I will not change actually, Vishal. I see we because we have globally initialized I. You see, we have globally initialized I outside of our function. So value of I is now not restricted to that function. Value of I is not restricted to that function. It's globally changing. Yeah. So that's why I is the value of at the second previous node, it's not 325, it's 290 based on the pre I minus 1. We are just looking with the previous value. Okay. So yeah, so now guys, we have already considered two elements. We have traversed this right as well. Now this right has only left for the last element. So now this right we will also traverse. Okay, this right will also travel. So now you know that pre I minus 1, that would be the first value. So right now I is at 4. Right now I is at 4. Correct? We are looking for 4, right? Fourth element. So again, I will be 3. We will be looking here 530 comma infinity because max is infinity here. So 530 comma infinity. So yes, with this case, it will be passed. For this case, it will be passed. Correct? Because 960, we are looking for what? I is equal to 4 and 960. Guys, you do not need to like think about that from where these logics are come from. You just need to for deciding min and max, you just need to look for this value pre I minus 1. And always these max we are already passing it out. So always you need to look for pre I minus 1 while you are updating your range for min and max. So that's what will give you answer. So now I is equal to 4 and value is 960. Okay. And now what we'll do, we'll again check for this. So I'm just drawing this part here, guys. Just drawing that part here. 530 comma infinity and we are looking for I is equal to 4 and value is 960. 960. Okay, so this time it will pass the condition, and once it will pass the condition, it will go into the left side again. It will go into the left side. Correct. Once we are passing the condition, we are going to the left side. Now I value will become 5. Now I value will become 5. This I will become 5, and the range would be I minus 1 comma minimum comma I minus 1. So the range would be 530 comma and 960. Correct. But we are not looking any element here. So we are not looking any element here. So that's why we will simply return false here. That's why you can see this first condition as well. If I greater than is equal to n, because now I has become 5, which is equal to number of elements in the pre-order. So that's why we'll simply return false from here. So now this will return false. Same goes for right. It will also return false. So for this scenario, guys, 960 will also become the leaf element. 960 will also become the leaf element. Correct. And now it will this both will return false. For this both will return true. So this condition true and false. It will also end here, the first condition. And that's what happening in code as well, guys. You can see the whole code now. Whatever we did, that's all written here. This is one way. There is one more approach to solve this problem. That is with stacks. That is with stack. If you want, I can talk about that in revision class. That's a different approach through the iteration, where we need to push some element into the stack. Then we need to delete some element from the stack. That's another approach. But did you guys understood this approach? For updating the min and max value, you just need to look for pre I minus 1. And then wherever we are not finding any left and right, we are saying that that's our leaf node. Correct, guys? Anywhere you guys stuck, let me know in the chat. What about others? Hariharan, Joseph, Harsa, Arad, Suraj. So if you guys want, I think I can discuss this in a revision class as well with stack approach. Okay. So now let's jump into the next question, guys. Now let's jump into the next question. So question 4 we have already done. Now this is the next question for us. Very interesting question. Given a binary tree, flatten the tree into a linked list. Flatten the tree into a linked list. And the linked list should use the same nodes where the right child is pointing towards the next node in the list and left child pointer is null. So guys, you can see this question where they have given one binary tree to us. So now they are saying we need to flat this binary tree, and the condition is very similar that all the left node should automatically come to the right side. And we should not make a new list or anything like that. We have to use the same tree. We have to use the same tree and then do the changes there. Okay, guys, we have to use the same tree and then do the changes there. So that's what you can see. So 1, then we are going to the left side. You can see 2 is coming. So first we'll take that 2 here, and you can see 2 is coming there. Then 3 is coming here. Then 4. So you can see all the left side of 1 is now on the right side. All the left side of 1 is on right now. It's on the right side. 2, 3, 4. And then at the end 5, 6 is coming. So that's what they're saying, where the right child is pointing towards the next node in the list. Always, so the simple meaning is all the left node will be now moved to right side. Understood the question, guys? All the left node in sorted manner. Yes, sorted manner we can say, but no, sorted manner doesn't matter here. The because it's a binary tree, so we can say pre-order traversal. Pre-order traversal for this tree and that tree. After converting into the flatten, both should match because uh, in the in the pre-order we always look for root left right, so root is already going to be same, all the left is going to be null, we are only going to look for right side, we're only going to look for right side, so it would be pre-order. Right now the elements has given in this way, that's why you are going saying, so Joseph, it's in the it's in the sorted manner. So for solution for this would be, we will be start traversing from the left side, and once we got the left side node, we will add it into the parent right. So the solution for this would be, we'll start traversing from the left side. We'll first go for root, go for the left. Once we find out the first left, take that left, put it into the same nodes right. Put it into the same nodes right. Then again, if this node also has left, put it into the again. That is the next step. Let me tell you the solution for this. But first, before that, did you guys understood the question now? All the left element has to be on the right side now. Correct? And we'll do. Did you guys understood? Let me know in the chat, guys. Did you guys understood this question? Anyone has still any doubt? All the left element you can see 1, 2, 3, 4 has been come into the right side. They have been flatten it out. You just understand they have stretched it 1, 5, 6. They have stretched it and now they have merged this 2, 3, 4 there. That's what you have to do it. So Arad, what they have to do? They have to all the left side element has to approach will tell, approach will tell. So see guys, for this approach is not difficult, approach is very easy. So let's take the same example. Let's take the same example. So 1, 2, 3, 4, 5 and 6. We'll take one stack here. We'll take one stack here. We'll first push our root there. So 1 has been pushed here. Correct? So now 1 is here. Let's remove this line so we can easily remove the numbers. Yeah. So 1 is pushed. So now you know that we need to go into the next level. We need to traverse the next element. Correct? So what we'll do, guys, you can take stack or you can take queue as well. Yeah, I think, let me think about, we can take queue as well or not. No, actually, take the stack only. Yeah, take the stack. So let's first we push the root element, which is 1 here. Correct? Okay, that's fine. This is a root node. Now we will pop it out. Now let's pop this element. So now you can say now our while loop will start. So understand the while loop. Now our looping is starting. We'll say that stack dot length is greater than 0. This loop will continue run that. Correct? So first we'll do the pop. So this 1 will come out. This 1 will come out. So now once this 1 will come out, now we need to push the next element, 2 and 5. We need to push the 2 and 5. Which element we want first, guys? Because this is a stack. Only the top element we can take out. Only the top element we can take out. So which element we want first? Because after 1, 2 has to come, right? All the left element first has to come, then right element has to come. So which element we want first? So pre-order is used to prepare the sorted order of BST element, isn't it? No, in order. In order is used to prepare the sorted order. So which element we want out first? 2. Yes, Joseph has said correctly. We want the left side out first because that's what we need to add. So we will first insert 5 because that has to come later, and then 2 has to come out. So that's why first we'll push 5, then we'll push 2. Correct? Now take the 2 out. Now take the 2 out. Now next element which we have taken out, which is 2. Correct? So now, once we are taking it out, we'll also check. We'll put, because we need to add this, right? We have to add this to 1. We have to add this element to 1. So what we'll do? We'll do, if our stack is not, again, under this while loop, we'll check this condition. If stack dot length is not greater than 0, if stack dot length is not greater than 0, just take the top peak element, which is 2, take the peak element and add it into the current node. Add it into the current node. Current node dot write, which is 1, right? Current node dot write is equal to stack dot peak or stack dot top. I'm just writing top here, or peak, and you guys can consider. Right? Top. Okay, so right now 2 is at the top, right? And we are still talking about the node 1 only. So first we have pushed the element. So right now we're talking about 1 only. So first we have pushed both of their right child and then left child. Then what we are doing? We are just checking if stack length is still greater than 0. So current node dot write is equal to top. So 1 will now point out to 2 because at the top 2 is there. Correct? And then current node dot left is equal to null. Current node dot left is equal to null. Correct? Current node dot left is equal to null. That's what we'll do. So now this 1 left will become null. Correct? So 2 and 5 has been pushed. Now again, take the 2 out from here and take it into one variable called temp or node. Then again check left or right. Yes. So first 4 will be pushed, then 3 will be pushed. Correct? Now again, take the stack peak, which is 3, and add it into the current node. So 3 will be added. And 3 does not have any left and right, then it's fine. We will not insert anything here. Now let's go for the next element, which is 4. 4 does not have any left, right, we will not push anything. And again, current node dot right is equal to 2 top. So 3 after 3, 4 will come here. 4 does not have any child, we'll go for 5. Correct? We'll go for 5, which is the top here. So 5, and then 5 has one child, which is 6. We'll insert 6 also. That's how the code will work. We'll simply continuously, let me show you the code also. It's very easy code. It's not difficult. Let me show you the flat. Can you see flat? And yes. You see, first I'm checking if my root is null, just simply return it, whatever question is asking. Then I've taken my stack, pushing the root element in the stack. Then I'm checking stack.length, popping out the first element, checking. First I'm inserting right element. That's why you can see that. Because I want the left out first. Then I'm checking the left, pushing the left element. Then I'm checking if stack.length is greater than 0, then just put current node.right is equal to stack top element and node.left is equal to null. And once we are done everything, stack is empty, at the end return the root as our answer. Was not an easy question? Correct? Everyone understood? Line 34. Line 34. Line 34. Yeah. So it's a stack dot length. Here we are checking if stack has any length. Stack dot length should be greater than 0. If stack has any of the element, add the node dot right is equal to stack dot peak. जो भी stack में peak element है, just add it into the node dot right. See, I'm not putting greater than 0 because if automatically takes, if stack length would be 0, it will not go into inside the if. That's why I'm not putting greater than 0. You can see here also. I'm not putting any node dot left is not equal to null, because if it's null, it will not let them enter it into the loop conditions. Understood? Yes, it was easy. Now let's see. According to the slides, it should be only one question, but there is one more question in the slide. A second homework question. Let's quickly discuss it and then we will go for break. Okay, so you are given a binary tree containing only digits from 0 to 9. What do you need to do? Each root to leaf path in the tree represents a number. For example, 1 to 3 represents the number 1 to 3. You need to find and return the total sum of all root to leaf numbers. So what you need to do, guys, you can see this is the binary tree they have given. You need to start from root. You need to traverse all the paths like 491, 495, 40, all the paths from root. And then whatever paths are coming, you just need to add them and then return the results. You can see 495 is here, 491 is here, and then 40 is here. If you'll add all these three, you will get 1026 as a sum. So you need to return the sum from there. Understood the question, guys? 495, 491, 490. Understood the question, guys? You just need to start traversing from root side and then add them. So, so you have one binary tree, Joseph. You need to start from root and whatever paths are possible, go into those all paths and whatever numbers are coming in that path, just keep those numbers together like a string, like 491, 491. Just add all these numbers, not like this, like 9 plus 4 plus 1, not like that. Just concatenate. In string we say that, right? Concatenate. So just add all those path element, just concatenate them, and once we have all the paths, then add them. Then not do not do concatenation, then add them as a numbers. That's what you can see. 495 has been concatenated. You can see 495. This is the first path from root to leaf. Then we have second root to leaf path 491. This is concatenated. Then 40. It's also concatenated. And then once we have traversed all the path, just add all the things 495 plus 491 plus 40. And then we got the final answer 1026. Yes. Understood now, Joseph? Guys, I don't think it was very difficult question because we are already traverse everything in the binary tree with your recursion approach or any approach. We are already traversing, correct? If you take in order, pre-order or post-order, we are already traversing it. We are starting from root and then we are going to the leaf node. Correct. So right now we also have to do the similar thing. We have to start from root, but we just need to add some more things into them. We just need to add some extra thing into that. So let's see. For this question, let me also open the code for that. So first we will take one array, guys. What would be the name of this question, by the way? Right path, some suit root leaf. Yeah, root leaf. Okay, so you guys can see that what we are doing, we are passing root, path, and answer, because you know why we are doing 1 minute, because we need to fetch two things: path from the root, path from the root till the leaf node, and then the sum of them. Correct. So what we'll do, guys, let me draw this the same example in then OneNote as well. So 4 0 9, what was the next? 5 1, 5 and 1. Correct. These are the nodes which we have. So see guys, first path is 4, 9 and 5. This is the path. Correct. So see guys, what we'll do, we'll start traversing from root node. We start traversing from root node. We will go to the left side. So we'll take one like a variable called path. We'll take one variable called path. And whatever root dot value is, we will start adding them. So first we are at the 4. So path will have 4 as a string because we need to do concatenate, right? So 4 will be the first element. Then we'll go for, then we will reach to left, which is 9. So 9 will be added. Now from here, two scenarios are there. This one left or right. Correct? Till now we are going into the left side only. Left, left. So now 495. So 495 has been added. Correct? Once we reach to next one left, which is the null. So once we reach here, just add all the path which we had here, 495. Till now, whatever path we have, just push it into one array. Just take the answer array that like that. So first will be pushed 495. Correct? Now this is the right side of it. We can take right also here also. We can check both scenarios. If both has null, right and null, then just push it. Again, go for here. So now the path, now it will be past two things, 491, right? Sorry, it will pass 49 only. It will pass 49 from here. 4 and 9. It will pass two things from here. And here, it will go to the its own right or left. It will be having 491. And add it into answer only. So 491. This is the second answer we got. And then we'll go for this right as well. Here it will be 4, 0 only. And same, we'll add 4, 0 here as well. And at the end, once we got all the path, we'll just simply add all these three. We'll simply add all those three. Let me also show you quickly the code. You can see in the sum leaf path, I'm passing three things. You can see root, empty string because it's for root, and then my result as an array. And then you can see if my root is equal to null, I'm returning 0 there. I'm returning 0 there. Okay. And then you can see if root dot left is equal to null and root dot right is equal to null, I'm just adding that current element, whatever root I am right now, and then pushing my answer into the answer array. Correct? And then you can see root dot left, and every time I'm passing path, whatever path I have come to, and root dot value. Correct? So first time empty string plus 4, right? Empty string plus 4. So here path will be passed. 4 will come here and answer as a empty array, because that's what empty array we are passing here. So here path will be empty string and root dot value will be 4. So empty string plus 4. That's what, guys. We're just traversing left. Once we reach to the leaf node, push whatever path we have traversed into the answer. Same goes for the right side, same goes for the fourth right as well. And at the end, once we have already got all the path, we are returning the sum. You can see at the end, we would be returning answer. Oh, we are not returning answer from here. Wait. Why not? We are returning 1 minute, guys. Sum is equal to 0. Result. Oh, okay. Yes. So we are passing result here now. So in the result, yes, that's the same result, right? So yes, then we are just simply using the reduce method of result array and just parsing because all the answer are in string, right? Then we are just simply adding them. Our accumulator and the current index, accumulator and current index, we are simply adding both of them, and at the end we'll get the answer. This is the logic, right? For adding any array elements, same logic is written here. I hope you guys have understood. It was also not difficult. We just need to traverse from root till the leaf node, and just we need to pass one variable for tracking the path, like whatever node we have traversed. And we are pushing it into the, once we find out any leaf node, push all the path to an answer array. And then at the end, once we have the answer array, just use any of the array methods, not the reduce. You can simply put the loop into result array and then get the answer. Hope everyone understood this. Anyone has any doubt, questions, queries? You guys understood? Code, okay. This is the code only. This is doing whole things. Any line which you guys see as a difficulty? No? Okay, so now we can go for break and then we can look for the next questions. So now, right now it's 9:45. Let's come back at 10 o'clock. Okay, guys? Now let's come back at 10 o'clock. Is everyone back now? Great. So let me share my screen. Okay, so that was all question from the previous class. Now talk about the slides questions. Okay, you guys are able to see my screen? Anyone reply in the chat? You guys are able to see my screen? Yeah, great. So let me first pick the easy one. Then I think we can go for the tough one. Yeah, I think this one is easy. Given a binary tree, find a path from root to any given node x. I think we have already done the previous question in similar way. What do you guys say about it? So we need to find a binary tree, find a path. Sorry, in a given binary tree, we have to find a path from root to any given node x. So like they have given, and they are saying you need to find the element 5. So once we reach to 5, we just need to find out the path. What is the path? We have it here. So like similar way, we can take an array, or even we can take a like if you want to go with the iterative approach, we can also take the iterative approach here as well. Even like once we reach to the 5, to that final element, what earlier what we were trying to do, we are trying to look for leaf element, right? So here we do not need, here we will be looking for leaf element. So once we got the leaf element, we will be removing that element. See, uh, I think it would be better to take a stack here. So let's go with the iterative approach here. Let's go with the iterative approach here. Okay. So let's draw this very quickly. 1, 2, 4, 5. What else is there? 3, 6, and 7. And our element is 5, which we need to find it out. And our answer is, if we try to find out the 5 here, so from root, the path is 1, 2, and 5. So our answer is 1, 2, 5. Hope everyone has understood the question. Everyone understood the question, guys? What about others? Let me also open the code for it. Okay, so Joseph question is very easy. We have given one binary tree. This is our binary tree. we will be giving this binary tree and one element, which we need to find it into this binary tree. Correct? And while we are finding it out, if that element exists, you need to tell the path from root. You need to tell the path from root to that element. That's what the question is. So element is 5, then path would be 1 comma 2 comma 5. If element is 3, the path would be 1 comma 3. If element is 6, the path would be from root, it would be 1 comma 3 comma 6. So that's what our answer is, 1 comma 2 comma 5. Understood, Joseph? So we can see, guys, it's an easy question. If we just take the stack here and if we simply traverse our element, like first push 1, go for the left side, push the 2, correct? And 1 minute. Uh, mhm. Yeah, I think go for the 2 and then go for the 4 left element, right? And because now we got the leaf, now we like get the leaf, just remove it. Just remove that element. Now go into the right side. So once we go to the right side, we got 5 here. And once we got it, that should be our answer. Whatever the stack we had till now, that should be our answer. So what we are doing here, we are just traversing into the left side first. Left root, left. Once we reach to the last element, we are removing the, we are popping it out. And once we are, and same, see, same will go for, like if we are trying to find out 6, let's try to look for 6, guys. Let's try to look for 6. We'll take same stack. We start with 1, correct? First we'll insert 1 here, correct? And now we'll go for 2. Now we'll go for 4, correct? All 3 conditions when we got the we got the leaf element here, correct? So once we got the leaf element, we'll remove 4. Now we'll go for the right side, which is 5. So we'll insert 5. Again, it's not matching. Again, we got the leaf element, remove it, right? Remove it. So now once we remove it, now we need to go back, right? Now we need to go back, and now we'll from the stack we need to remove 2 comma 1 as 2 as well, because we have already traversed its left and right. We already traversed left and right, so we do not need it longer, because left and right both are giving false to us. So we'll remove 2 as well. Now we'll go for one's right side, which will be 3, right? So now for 3, it is still not matching. Let's go for 6. It's matching. So this would be our answer. Let me show you in the code as well. Same approach would be here for the code as well. So what would be the question? Find find x. Yes. You can see, guys. This is the. I think they are doing it in the. Yeah, they are doing it into the recursion with using one stack. Yes. So we are using a recursion with an stack. We have like a stack or array, whatever you want to say that. You can see, because we are using the stack methods push and pop. You can see anything. By the way, yeah. So logic is same. You can see. So first we are pushing into the data, and wherever we are finding that element, we are returning true, right? And if not, just look for the left side and then look for the right side. If anywhere we find it out, anywhere we are finding out, we are just simply returning true. If not finding it out, just pop that element. But see, we are popping it into two situations. First, we are popping it out when we are not finding it on the left side, and we got the leaf node. When we got the leaf node, so we will be popping out that element as well. And second time we are popping it out when we do not find it on the left side, we also do not find it into the right side. In that scenario, also we are popping it out. That's what the code is. Every time we are pushing it into, and once we are not finding it out that element, we are popping it out. And in any of the left subtree or right subtree, once we find it out that element, in those scenarios, this recursive call will return us true, and then we will be returning directly from there that answer, returning the true. And at the end, our answer would be saved in this array. We can return our answer as an array. This question was easy. That's why I have taken it first. Did you guys understood this? This is the answer. This is the answer array. You just print it out. You will get the answer. Because that's why that array is outside. Okay, Joseph? You will get your answer here. You know that, right? This is our answer in the stack. Everyone understood it? Where is has path? Has path is not there. What is this different function name? Oh, different function name. Okay, 1 minute. 1 minute, guys. This is the same name. Has path. Where is the first case we are popping? This is the first case, right? So first, you can see, first we pushed our stack. First we pushed our element 1. Then we are going for left side. Once we didn't find into the left side, and also on the root side, also on the right side, we're also popping it out. When we are not finding on the left side, we're not finding on the right side, we're just popping it out. Checking on the left side, checking on the right side. Once we have already gone to the left side, you can see once we reach to the leaf node, at that place, both the left and right would be null, right? It will return false. So has path for left, has path for right. Both will return false. And then we will be popping out that element. And then we will going from there to the back side. So in this example, so first we will reaching to 4. So 1, 2, 4. All these three elements would be here, 1, 2, 4. Now, because has left has given us has left for 4, just for 4, has left has given us false, has right has given us false, we'll pop it out. We'll pop this 4. Now we look for 2. Now we look for 2. So this one has given us false. Let's look for 5. So 5, again it will be pushed here. First we'll remove the 5, then we'll remove the 2. Both will be giving us false. Everyone understood? Can we move into the next question now? Yes? Let's see, is there any other easy questions we have? LCA. Yeah, actually this question we can take because this question is going to solve 2 questions. Yeah, so let's take this one. What is the last one? Target node interval K. Merit that have distance K. This one is little bit that one, but yeah, let's start 3 and 4. Then we'll look for the first one. Yeah, let's start from 3 and 4 because this 3 and 4 are totally related. So we'll complete one question, we'll complete the second question as well, fourth question as well. Okay. So now, guys, they are saying that we have been given a binary and 2 nodes. In the input, we will be giving 3 things. One first as a binary, second input, 2 more inputs will be there, which would be 2 nodes of that binary. Okay, and we need to find the lowest common ancestor between them. We need to find the lowest common ancestor between them. And according to the definition of lowest common ancestor in the Wikipedia, the lowest common ancestor is defined between 2 nodes P and Q as the lowest node in the tree that has both P and Q as descendants, where we allow a node to be descendant of itself. Okay, I know this could be a little bit difficult to understand, so let me draw it. Let's take the same example. 3, 5, 1, 0, 8, 6, 2, 7, 4. So guys, when we talk about the ancestor means our parents or grandparents, like all of our parents, like the continuous, like whatever our parents or their parents, those all of our are our ancestors. And when we talk about descendants, it means all of our childs. From my, probably if I talk about the my generation, so whatever my generation is there, that would be all of them would be my descendants, right? That's the meaning of ancestors and descendants. Okay, so now they are talking about the lowest common ascendants between those nodes. So now there would be two nodes that would be given here. We need to find the lowest common ancestor. Lowest common ancestor. Lowest, array, 1 minute. Let me erase it. Yeah. So lowest common ancestor. Like if they are giving for, let's take the example of 6 comma 4. If these are two nodes, you need to find it out the lowest common ancestor for these two nodes. So lowest common ancestor is, guys, so uh, the closest one. Just start traversing from 6 and 4, whatever the the lowest common ancestor. See, for 6 ancestors are, for 6 ancestors are 6 itself, 5 and 3, because here root starts 6 comma 5 comma 3. And for 4 ancestors are 4 itself, 2, 5 and 3. But we need to find it out the lowest common ancestor. It means whatever is coming first, like from here, whatever is coming first as the lowest common ancestor, that will be our answer. So in this case, 5 is the first one who is reaching first from while we are traversing from 6 and 4. So that's why 5 would be our answer here. That's why 5 would be our answer here. Now let's take some more example. Let's take about 2 and 8. LCA for 2 and 8. So now you can see ancestor of 2 would be 2 comma 5 comma 3. Ancestor of 8, 1 comma 3. So 3 would be the first who has been the common ancestor for both of them. Right? Now let's talk about 5 comma 7. LCA 5 comma 7. 5 comma 7. So you can see 7 ancestor are 7 to 5. 5 ancestor are 3 comma 5. So the common one which is coming first is the 5 itself. So the answer would be 5 here. I hope you guys have understood what is the meaning of LCA here. That's what the Wikipedia says. That's what the Wikipedia says. You can see the last line, where we allow a node to be descendants of itself. It means it could be ancestor itself. Lowest or first, yes, first common ancestor. Yes. That's also Hariharan has given the correct, yes. First common ancestor. If we are traversing from the right side and right side or left, like we are traversing back from both of the nodes to the root side. So first, yes, first common ancestor. Yes. Everyone understood the question? So now let's try to solve this question, guys. Let me also open the code for. Okay. So now let's think about it. Okay. So now let's think about it. So for finding it out this guys, so what we will do, we'll start from last node. Let's just thinking about, let us start from last node. So for 4, 1 minute. 1 minute guys. Mm, hmm. Oh yes. So let's start finding for 6 and 4. I was just thinking about which way I should start explaining it. So let's start for 6 and 4. That's the first example, right? They've given two notes to us, 6 and 4, and this binary tree. Okay. So our input was binary tree, this binary tree, and our input was like we can consider P and Q, two nodes they have given us. We need to find the common ancestor for these two nodes. Correct? So yeah, so that's what I will do. Okay, so let's start traversing from 3. So first we'll see, guys, wherever they are matching, wherever our elements are matching, we would be returning that node from there. We would be returning that nodes from there. 1 minute, let me draw a little bit more, guys. 1 minute. I think it will little bit confuse you. Let me draw a little bit more elements here. Then we'll make little bit like good answer, I'd say. So it is 3. Just randomly taking it. It like let me just take another number 9. Because this is binary tree, anything we can take, right? 9. We can take 11, 6 here, and we can take 11 here. Yeah, correct. But yeah, our answer is still same. So 5 would be our answer here. Correct? But yes, little bit change will be there. Just in the logic I want to explain you. That's why actually I was just trying to do that. Yeah. Okay. So guys, let's start from leaf node. Let's start from leaf node. Like we will traverse to the left side, but let's start understanding this question from the leaf node. And this could be anywhere. It's not like that because we have taken the just logic. Try to understand this logic from leaf node. Okay. So see guys. So once first we will compare each node will compare with the P or Q wherever they both match. These both values I got. Wherever I got this value, I will simply return that node. I will simply return that node. And if we do not find that, if we do not find that, and if we reach to null position like this, for this, it will be null left and right. Correct? If we reach to this position, we will be returning null from those from those nodes. So two scenarios only. Once we reach to that element, once we reach to that element, we will be returning that element only. And this will only happen once we got the 6, like whatever we are looking, if we got that element, we will be simply returning from there. We do not need to go any further down. Okay. But if we are not reaching to that element, like we are traversing onto left side, but somehow we are not like if we are not looking for 6, if we are looking for 0, somehow just understand if we are looking for 0, so we will first start traversing from left side, but we did not find 0 anywhere. So what we'll do, we will be returning once we will reach to 6, will we start returning null from there. Okay, did you guys understood what I'm trying to say? once we reach to the Once we reach to the leaf node, and if we are not able to find out the element which we are looking, we will be start returning null from there. Is it somehow related to intersection of linked list? No, it's a little bit different. Did you guys understood the last line which I told you? We will start traversing, and once we reach to the leaf node, but we are not able to find out the element which we are looking. We are looking for 6 and 4, right? That's the two nodes which has been given to us in input. 6 and 4. But we are not able to find them into the left side. So what we'll do, and we reach to the leaf node. So what we'll do, we will be returning null from there. I will tell you the answer for that. I will tell you the reason. But let's understand, we are starting returning null from there. Okay? And once we are reaching to that element, we will be returning that element from. We will be returning that element. Understood, guys? So that's what you can see in the code also. The first line is saying that if current node is null or current node is P, means the element which we are looking, or current node is equal to Q, just return that current node. Just return that current node. Okay? Just return that current node. Understood, guys? So that was the first line of code. So now let's look for 6 and 4. So for 6, we have reached to the element. Because that's what we are looking, and somehow that element was exist in the left tree. So we will be returning 6 from here. And we will not go further. If there are, like, if I am telling you, if there are 2 more elements, 2, 3, we will not go there. We'll simply return from here 6. Okay, now we are return it from here. So for 9, 9's left is returning 6. Now let's go for 11. So 11's left and right both are null. 11's left and right both are null. Correct, guys? Both are null. So 11 will also return null. Correct? So when left and right, 11 will also return null. Are you guys getting not? 11 will also return null. Are you getting it? Why 11 is returning null? Correct? So now, guys, now let's look for the next logic, which is if somebody's left is returning 6 and if somebody's left is returning null, in those case, you need to return for 9, 9 will return that number which, like, whatever the node we are returning. So 9 will also return 6. So see, guys, there are only 3 cases. One case when the leaf node is there, and those scenarios we need to return the null. If we find out the number, we just need to every time return that number. So you can see on the 6, as we find those 6, we will be returning 6. But for 9, left side is returning the number, but right side is returning the null. So in that case, you will be returning the number. Okay, in that case, you will be returning the number. So now you can see 5's left is returning 6. So now let's look for 5 right side. So now let's look for 2. So we are reaching to 2, but we have to traverse again. We will be going for 7. So 7 is again going to return null. Correct? 7 is again going to return null. Am I right, guys? 7 is again going to return null. Everyone trying to follow me or not? It's not difficult question. It's very easy question. You just need to understand the logics here. Whenever we are reaching to the leaf node and we are not able to find out the number, just return the null. Will that happen generally every time in case of number in null? Yes, it will happen. Returning number. Yes, number. It's not number. It's a node. You are returning that node. It's not. I am telling you 6 here, but it's a node. The node you are returning here. Okay. Okay, Ariel. You can consider it as a number also. So you are returning number. If they are asking about the number, you can simply return number. Otherwise, you can return the node as well. Okay. Okay, sir. But why null is not returning? I didn't understand your question. Why null is not returning? If we find out the number, we have to return that number. If we are not able to find out that number, we will be returning null. In 9 place. In 9 place, that's another logic. That's the second logic. In 9, if one left side of it is returning any number, and if right side of it's not returning any number, we will be returning number at that place. Understood? See, there are only two logic. If somebody's left and right is not returning anything, we will be returning null. If somebody's left or right is returning anything, we will be returning that number. Yes. And sorry, for everyone. If somebody's left and right is not returning anything, we will be returning null at that place. If somebody's left is returning anything or right is returning anything, we will be returning that number. Understood? And third logic is if somebody is see, there are only three scenarios, right? First scenario, if any nodes left and right is not returning anything, that's the first scenario. Second scenario, if any nodes left or right, any one is returning. And third scenario is if anyone's nodes left and right both are returning. Correct? These are only three scenarios. Is there any more scenarios? You guys tell me, is there any more scenarios apart from these three? First scenario, any nodes left and child are not returning anything. It means they are returning null. Second scenario, any parent nodes left and right is returning, one of them is returning something. And third scenario, if any parent nodes are returning both left and child, both are returning. Are we good with all these scenarios? All these three scenarios, Hariharan and Suraj, Arad, Joseph. Are we good with these three scenarios? If you have understood these three scenarios, you have solved the question. Only these three scenarios are there. In all these three scenarios, we have to return something. In the first scenario, when left and child are not returning anything, in that scenario, we are returning null simply. In the second scenario, when one of the child is returning, when one of the so Joseph, have you understood all three cases? When any parents child, both childs are not returning anything, one of the child is returning anything, both of the childs are returning anything. Have you understood those all the three assumptions? Yes. So now that's what in the next part I was explaining. Once you have all these three scenarios, in the first scenario, like this, like the leaf node, this 11, it is, you can see, is left and right childs are not returning anything. They are returning null. So 11 will also return null. But in the case of 9, one of the right child of 9 is returning null, but left child of 9 is returning 6. It means in this case 9 will return 6, not the null. But in the case of 5, let's understand 7 first. So you guys tell me, for 7 what it will return? 7 will return null, right? What about 4? What 4 will return? What 4 will return? 4 will return 4 because it is matching with the value of q. It's matching with the value of q. So it will be returning 4. So now you guys tell me 2's left is returning null, but 2's right is returning 4. So what 2 will return? What 2 will return? Yes, it will be returning 4. Correct. So now this is the second scenario. This is the third scenario. This is the third scenario. When left and right both are returning. When left and right both are returning. In that scenario, guys, you need to return that node, this node. You need to return this node. And this node would be our answer. You just simply need to return this node. Wherever you find it out that left and child both are returning, it means that's the first ancestor, because at that place both of trees are merging or like meeting. So that's the first point where where our answer will be there. The answer will be, we will be getting answer there. That would be the first point. It was not difficult at all question, guys. This was not difficult. You just need to understand the logic. There were three cases. Yes, this was typical logic. There were three cases. In all these three cases, you just need to return something. In the leaf node scenarios where you do not find the answer, you just need to return null from there. And when you have a child which is returning something, when one of the child is returning something, not null, returning some numbers, in those scenarios, you need to take that number, not the root node. And once both of your child is returning, you just need to return that as the answer. And that's what is happening in code also, guys. You can see this is my base condition where I'm checking if my current node is null. It means this is the leaf node scenario. So just return that current node, means return null. If my this is the single child scenario, if my current node is P or current node is Q, it means they are matching. At that time also return the current node, but this time current node will not be null. This time current node will be that particular node 4 and 6 in our example. So we'll return current node. Otherwise you can see I'm just simply traversing every time to left, then using my base condition to go come out of it, then I'm going for right, then using my base condition to come out of it, and then I'm checking. this is for this is for returning left and right. When one of the if left is equal to null, then return the, because if this condition has not passed, if this condition has been failed, it means now we are at the, if this condition has not passed, so now it means we are at the 9 or 2. So in these conditions, I'm checking if left is equal to null, return right for that node. Else if right is equal to null, return the left there. But if both are not there, it means we have reached to our answer. It means we have reached to the 5 node. It means both are returning something. Both are not null. It means 5 left is also not null and 5 right is also not null. It means that's our answer. And we will be returning root from there. Returning the root from there. This will not be root, by the way. 1 minute, guys. This would be current node, not the root. Yeah, this would be current node. Yes, this would be current node, right? Not the root. Yeah, it would be current node. So I hope you guys have understood this question and the logic as well. It was just the logic to understand. Sir, what would be the case of both are null? Say both of null, this would be the scenario, right? Current null is equal to null. If left and right both are null, we have already written the null from there. We are already returning the null from there. So see, if we reach to 4, right? So at that case, so current node will also be null because that's left will also be null. So in that case, we are not returning anything. You can see, not returning anything in that case. We are simply returning the current node. Or we can actually, okay. Oh yes, if that's the case. See, still this will pass, right? Who was asking that? Hariharan. If that's the case, still it will pass, right? If left is equal to null, still it would return right, which is still null. Understood, Hariharan? It will go into the first condition. It will return right, which is also null. Okay, so second question is also okay. The second question is also very similar to that, guys. Very similar. Let me tell you. The fourth one. For the find the distance between two nodes in a binary tree, and the distance between two nodes is referred to as the minimum number of edges to be traversed to reach one node to other node. Minimum number of edges to be traversed to reach one node to other node. So like you can see in this example, 7 to 6. So the minimum number of edges for traversing 7 to 6 will be 1, 2, and 3. Why it is giving 2? 1 minute. So one, what are you saying? This only two node is referred to as the minimum number of edges to be traversed to reach one node to other node, right? Here we have seven and here is six. So one, two, three. Yeah, this answer looks doesn't look like doesn't look correct. Yeah, this answer is not correct, guys. Seven and six. It should be three. Let's look for 4 and 8. Is it the correct or not? 1, 2, 3, 4, and 5. Yeah, for 4 and 8, answer is 5. But for 7 and 6, answer is not correct. You guys can see that, right? We can only reach through like this only, right? 1, 2, and 3. They are saying the minimum number of edges to be traversed. We can't directly reach to 6 with 2 edges. Right, guys? So that's what the question. Yeah, wrong answer. Did you guys understood the question? We just need to, they will be giving us again two nodes, again the binary tree, but we just need to find it out the minimum number of edges to reach to first node to second node. So do you guys see any similarity here? If we have the same question, this one, 5, 9, what is happening? 9, 6, uh-huh. So it's not now erasing, it's not erasing. Huh? Sometimes it just behave its own. 5, 9, 6, 2, 3, 2, 4, 7. Oh, 3 was also there. 3, 1, 0, 8. So now guys, if we want to find out the distance between 6 and 7, what would be the distance here? It would be 1, 2, 3, and 4. Correct? That would be the distance between 6 and 7. Am I right, guys? Let me mark the path here. So 1, 2, 3, and 4. Correct? So 4 edges will be used for that. So guys, can you see a little bit similarity here with the previous question which we did? Anyone can relate it with little bit with the previous question? Same returning. So see guys, the the reason for this is why I'm saying it's going to be similar to that. It's because you can see again we are returning, like we are counting it from the LCA only. If we just find it out, 6 or 7 LCA would be 5. Correct? So LCA of 6 or 7 would be 5. And then we just need to find out the distance between from the LCA to the 6, distance from LCA to the 7, distance from LCA to the 6, distance from LCA to 7. So distance from LCA to 5 to 6, LCA or distance, whatever you want to write, distance from 5, which is LCA to 6 is 2, and distance from 5 to 7 is also 2. So just add them, we'll get the answer as 4. Get the answer as 4. So that's what guys we are going to do for this question. We are first going to find it out the LCA for them, and once we find it out that LCA node, we will be just running two loop finding out the distance. Distance is very easy. Just go into the label wise. Let's go into the level wise. Yes, just go into the level wise. Level wise, or just take a variable while you are traversing, just add it. Let me show you. I have the code for that as well. for finding out the distance. So if I go for this one, LCA distance, so first let me correct this current node here. So this is the code which I used for LCA, calculate same code for LCA, no changes, same code for LCA. Now, this is the find distance. So first you can see, first we have find it out the LCA, then I'm just traversing like A to 0. This is like starting distance. I can write it distance also. I can convert this all label to distance, not a problem. I'm just writing a label, you can understand with distance as well. And then B to LCA to B, and then adding this term. And you can see in the find label, I'm just simply using the recursion here. You can see. So what I'm doing here, if root dot value is equal to A, return the distance. And while we are traversing to the left, we are just doing distance plus 1. Distance, we are traversing to right, distance plus 1. Correct? And then we are returning it out. Very simple code, right? We are just find out that element, whatever label we have traversed, we are just adding it in, or depth you can say, or level you can say, we are just adding them. Just see once the code. So once we have not find anything in the left, once we did not find anything in the left, then only go for the right side. That's why you can see if left is equal to -1 and left is equal to -1 will only happen when we reach to the leaf node. Once we reach to the leaf node into the left side. And if we do not find anything in the left, then we'll go for the right side. And once we have already traversed everything, we have not got anything, it means we just need to return the left one, which is -1 only. We will return the -1. So we are returning, we are just checking it. First, we are checking all the left side. And if we already got the answer into left, if we already got the answer in left, then why to go for right? Understood, Hariharan? If we already find out the answer on the left side, then why to go for right? That's why I'm just putting it. And we will, when we will not able to find out the answer in left, once we got left is equal to -1, it means we have already reached to the last node. At that time, we will be not be able to. That's where we will return the left as -1, and that's where we will be checking the condition. Correct, Joseph? That's what we are doing here. We are starting our route. We are just going to the left side, continuously going to the left side, every time checking all the left values. Is it matching with the A? If yes, return that level. And you can see every time I'm going left, I'm increasing my level as well. So level 0, level 1, level 2, level 3. And if we are not able to find anywhere it is, it means left to be at the end, we got the leaf node, we will be returning -1 there. And once we are returning -1, we are going to check for the right side. And you can see level will not change this time. It's not, level is not global variable. Let's, level is here, the local variable. So level will still be 0 here. You guys can understand, like level, we have already increased it. Now level will be 4 here. That's not right. Level is here, it's a local variable, not the global variable. Like I, when we were doing the leaf question, at that time I was the global variable. So if we are updating it one place, it's going to update everywhere. But here we are not doing that. You can see we are not assigning label back. It's just we are adding it and again passing it as a number. We are not passing the reference. We are just passing the value. Why at last we are returning left, not returning right? Why at last we are returning left, not returning right? We are returning both. You see, we are returning both. Hariharan, we are returning both things. Left is equal to -1. Yes, Joseph. We are doing that to telling to our code that in left side we have not find anything. So now go for right side. So that's why we are doing left is equal to -1. And then later on, we are not left is equal to -1. We are returning -1. And then we are checking. If we are not able to find out anything in the left side, then go for the right side. Understood, Joseph? When we are not able to find out that element into the left side of tree, then I'm saying now look for the right side. If we have already find it out on the left side, then why to go for right side? Already told, right? So that's why we are putting it left is equal to minus 1. I hope you understood. Joseph, you understood why we are doing left is equal to minus 1? Because we do not want to go for the right side. If we have already find out the element, we have to distance from right and left. Add. We have to add the distance from right and left. From right and left. No. That's what we are doing in the bottom. You see? Once we find it out the element, we are adding the distance at the bottom, not on the above function. On the above function, we are just finding out the distance. Understood, Joseph? Yeah. So LCA to P, LCA to B. If we have P and Q, so first LCA to P, then LCA to Q. Then we are adding them at the end. Understood, everyone? Now let's look for first question. LCA would return 5, right? LCA would return 5. Yeah, LCA would return 5, correct. Yes. In our example, LCA would return 5. So why function name is recurse tree at top. At top. Where? Anything, anywhere function name is wrong? LCA function. Yeah, it's LCA, right? Oh, you are saying LCA. LCA function. Ah, okay. Thank you, thank you, thank you. Thank you for pointing it out. Yeah. Thank you for pointing it out. Yeah. Thank you. I corrected it. Thank you, Hariran. Yes, and we find distance from M left subtree and right subtree. Yes, so first we find out the LCA, then we find the distance for from LCA to P, LCA to Q, and then we add them, Joseph. Okay, understood, guys? Hariharan, Joseph, understood? You guys understood? We traverse left side and right side. We traverse left and right both. Yes. In the distance function, we traverse both left and right. So we have one LCA node. You have not you have understood, right? This part we have this LCA node. This is LCA node, right? And this is our P. This is our Q. So for LCA, we are traversing this. From LCA, we will traverse this side, and it can traverse left and right anywhere. From 5 also will traverse this side. It will traverse. You can see first it is traversing right, then it's traversing left. So it can traverse both sides from LCA. Understood, everyone? Is there any other doubt you guys had? No. Okay, so let's quickly understood the logic of first question. That's also interesting. Okay, which is we have been given pre-order and in order, and we need to construct the binary tree. Okay, we have been given a pre-order and in order. So like our pre-order looks like this: 3, 9, 20, 15, 17, and our in order looks like for the same tree 9, 3, comma 15, comma 20, comma 7, comma 7, guys. Okay, this is our, this is the two input they have given to us, and we need to construct a tree based on these two inputs. So what is the logic for pre? What is the logic of pattern pre follows, which is root, left, and right. Correct? What is the pattern in order follows? Left, root, and right. Correct, guys? Did you guys ever understood the question? What we need to do here? So we have been given two arrays which are having pre-order in order, and we need to construct a tree. Okay. So guys, what we'll do, first let's take 4 pointers. One is this one. We can write it as a low position, and this one is a high position for pre-order. We can say PL, PH, just for considering. For in order, IL and IH, just for tracking the low and high position of our arrays. Okay, so now guys, as we know that in pre-order, always first element is going to be our root. Correct? In pre-order, as we know according to logic, the root element is always going to be at the first element. So we know that 3 is going to be our root. Right, guys? We know that 3 is going to be our root. Now we need to find it out our left and right elements. Correct? In binary tree, left and right element can be there. Always, right? Left and right would be there. Now we need to find out left and right element because it's not BST. In BST, we know that there could be left, there could not be right. There could be left, there could not be left. Because if it's the lesser then it's left. If not, then it will go to the next number will go into the right side. But in BST, we need to traverse left and right. Right. So now for finding out its left, what we'll do, we will find it out this particular element in the in order array. So we'll find it out this 3 here. So now we know that in order follows left, root, and right. It means all of left of it would be left. All the left side of it would be left, and all the right side of it, this all would be the right side of a tree. Correct? So this 3 has told us that 9 is going to be left side, and right side it is going to be 15, 20, 7. Am I right? You guys understood? Yes. Now we just need to use the same logic, everything same, again into these two subtrees. Again, we need to use the same logic in these two subtrees. So now 9 would be again the root here. 9 would be again the root here. Correct? But it does not have any left and it does not have any right because we have already traversed 3. We have already traversed 3. So it does not have any left. It does not have any right. So 9 will be here. Correct? And same for 15, 20, and 7. Same for 15, 20, and 7. So again, we'll check here. The third element, which is 20. So 20 will be our root here. In this case, 20 will be our root. So 20 will be our root. And 15 and 7 we can check from here. So 15 would be our left and 7 would be our right. So I think the final binary tree will look like this. 3, 9, 20, 15, and 7. Let's see if this is our answer. 3, 9, 20, 15, 7. Correct, guys? Have you understood the question now? Understood? Everyone? Joseph, Hariharan, Arad, Suraj, Vishal, did you guys understood the question? So let's quickly understand the logic of it also, because I already explained the logic, but you just need to traverse all these 4 pointers in the recursive way. You just need to traverse all these 4 pointers while constructing your tree. Let me also open the log code for you guys. You guys can parallelly understand both things. Build tree, I think that's the question, that's the code. Yeah. Okay, so you can see, guys, in the build tree method, we are passing in the constructor method, we are passing these 6 things. So first is pre-order, in order, and then 4 pointers. And these 4 pointers, you can see that pre-order low, pre-order high, in order low, in order high. Understood? Then now, let's understood the code now. Understood, guys? We are taking 4 pointers and then 2 arrays. Okay. So now the first time we will first construct a tree node, because we know that 3 is going to be our root. We do not need any permission for that. 3 is going to be our pre-node. So that's why you can see here, you can see for the first time when we are constructing it, we are simply doing from the pre, take the first element, because p low is 0. You can see p low is 0. Right now p low is pointing out to first element, 0th element. So directly I have taken that as my new node, and just I am putting the value of that new node as this one. Now, what was the second step? We need to find this 3 into the in order. Correct? We need to find out that tree into that element into this in order. And we have the range right now 0 to 4. 0, 1, 2, 3, 4. And wherever we will reach it, we will take it like we will take that index as an element. Like we can take one index here. So for, like, just simply understand, once we find out the 3, once we find out the 3 once we find out the tree, we just need to find it out what are the element left on the what are the element left on its right side or in the left side. So that's what we are doing. Once we find it out 3, which is at the first index, what we'll do, we'll try to find it out. We'll subtract how many remaining element is there, what are the elements are left. So that's what, guys, you can see this code where we are trying to find it out, that pre-flow, like the the element 3, wherever it is matching with in order index. Once we find it out, we are finding out then what are the numbers left, and that how we'll find it out, si minus in order low. So it means, so if I'm taking si as a one index where it is matching Si as the one element. So first we are finding on the left side. So left side would be Si minus in order low. So it would be 1 minus 1 would be 0. It means only 0 element is on the left side. And for the right side, it would be uh, uh, it would be in order high minus Si. Correct, guys? In order high minus Si, which would give us, in order high would be 4 minus Si would be 1, which would be 3. Correct, guys? It will give us these 3 elements. Did you guys understood? Did you guys see? Just simply I'm doing the. So simply I'm just pointing out the pointers and getting the values. We have to see, Joseph, once we find it out the root, we have to find it out left or right, right? What are the elements we need to traverse? So that's why we are just doing these things. Si minus S, ILO. Si is the element. See, this is the element found. Just change the name. This name is not correct. You guys are not able to understand what is Si. It's the element found. Let's change the name. Element found. Wherever I'm using Si, element found. Yeah, element found. Okay. Now you understood, guys. Element found index. Also write index. Element found index. So this is element found index. And then once we find it out that element, we need to calculate how many elements are left. How many elements are left on the left side? How many elements are left on the right side? So that's why we are doing SI minus or element found index minus ILO. ILO is the in order lowest index. Now you guys have understood. Now you guys have understood. First we are taking element found as a -1. Then we are traversing in order array. Correct? Wherever we find that element, we are taking that index and then we are subtracting it with the in order low high, in order low. So that's why we got the one element on the left side. Got it? Now we need to create the left and right node. For the current root, we need to create the left and right node. So on the left side, we just need to again change our pre-order and post-order arrows. Pre-order and post-order arrows. So that's what, guys, it's happening in the code. You can see for the pre-order, what I did, P low plus 1. Right now I'm creating the left side node. So P low plus 1. So right now P low is 0th. So it will go for this one. So now P low will become this. For the left side, guys, P low will become this. Now P low will try to do the next operation from here. Correct? And P high will still be same. You can see, let me see. Okay, so P high is P low plus numbers left. Acha, P high is P low plus numbers left. So P high would be, guys, P low, because this one, which is the one index, and plus 1 minute, guys. P low is 0 or plus 1. Yeah, correct. Because this is the only element, right? 9, which is we're going to take for the left side. So that's why P low and P high both would be at same place for the left side. So that's why you can see the logic here. P low, pre-order low plus 1 and P-order low plus numbers left. And for the I1, for the in order low is still same. You can see in order low is still same. For 9, just check for 9. In order low is still same. So that's I'm taking in order as a 0. And for the for our in order high, element found -1. Element found at which position? 1. So element found -1, which is 0. So that's why you can see I'm just passing it that. See, guys, whatever is happening on the UI, same code is written there. For the pre-order, I just need to pass this element. So what I did for the lowest range, what I did, P low plus 1, pre-order low plus 1. For pre-high, what I did, element numbers left -1. So numbers left are 1 -1. So it will come here. That's what you can see. P low plus number left. P low plus number left. Sorry. Wherever P low is right now, it's in the 0th index. So plus 1 we did here. Same logic will work here. Now, if you want to construct the right side, so right side, it is for the pre-order, it would be, you can see, previous low plus number left plus 1. You can see previous low plus number left plus 1. So right now previous low it has 0. Number low will become 1. Number left is 1 and then plus 1. It will start from here. For right side, pre low will start from here. It will be previous low. And then whole. I think this time it will be whole, right? Yeah. P high is the whole. This is the P high. And for the in order, you can say element found plus 1. So yeah, element found is this position 1. So we need to take the remaining one. So element found plus 1. That's what is going into the right side. And this loop will continuously going on. Every time new elements will coming there. So you just need to understand, guys, what value P pre-order low and high, and what values of in order low and in order high we need to pass. That's what we need to understand here. And then this code will be easy. Just we need to understand, like, just take your pen and pencil, just try to understand which value we need to pass now. What part of array we need to pass now. And then we need to pass them. Automatically, next time the same thing will happen. Again, we'll find out the next element. Will find it under the in order array and find out the index for that. Understood, guys? Hope you all guys have understood the logic now. Anyone has any doubt? And I'm expecting you guys will practice it. Meanwhile, anywhere you are stuck in the coding part, you guys let me know in the chat right now. Guys, can you hear me? Joseph, Hariharan, Arad. Did you guys understood the part? The coding part? It was just, we need to move the pointers. Like the way we need, as we have seen while we're discussing about the logic, whatever the elements or part of array we need to pass, we can just simply find it out with the element found index. The element found index or the numbers left, that is giving us a lot of information. Those two pointers are giving a lot of information to us. Based on that, we can just construct our next array. Sure, let me push that. It's all in the master branch. Yeah, everything is in the master branch. So today it was whole session of problem solvings, and I think tomorrow's class I will request to Ansul that he could provide us class also only, or I think yeah, revision class is fine, where we will first discuss about remaining problems, and I will also request you to try out the last question which is left now. We have already solved all of the questions in the binary trees. Please solve remaining 3 problems also. 2 were in the assignments and 1 is in the last problem 4. So please try to solve those first and then try to look for all previous questions as well. And then in next class of ours, which is on Wednesday, on that day we will be discussing everything again. Okay, guys? So that's all from today, guys. Yes, we just need to practice. This see, Arad, these are not very difficult questions. It is very easy questions. You just need to catch the logic, and then you will be able to solve it. And like yes, they need little bit practice. Once you will do the practice, automatically these things will be easy catching to you. And I'm hoping when we will be meeting on Wednesday, I'm hoping everyone will be practicing more and more, and then we will be talking about these things very quickly. Okay, guys. So that's all from today. Let's Go for sleep and practice it more. You have whole day tomorrow on and next day as well. Good night, guys. Have a good night. Bye bye. We'll talk soon. Yeah. Bye bye.